Hi, everyone. Welcome to a continuation of Lecture 25, Part B. Um, Now we're going to move on to the definition of moment of inertia for a rotating object. And then we'll talk about the kinetic energy of a rotating object, and that and some additional formulas that apply to objects that are rolling along a surface or are otherwise moving through space while they are also rotating. Then we'll use I will solve a couple of the example problems in tutorial 25 that relate to these topics. And then you can try additional problems in the Mastering Physics online homework. So for the first of those topics, what is moment of inertia? Well, what we need is, let's think back to objects that are translating, meaning moving linearly through space. Remember that the role that mass played back in Newton's second law, F equals ma, or net force equals ma, mass had the role of being the property that an object has that makes that object more difficult to accelerate, right? In other words, harder to speed the object up or slow the object down or turn the object, all of which would be changes in its linear velocity. So those are all accelerations. The more mass something has, the harder it is to do any of those things. So it raises the question whether there is, for a rotating object, a similar sort of quantity that fully encapsulates what properties of a spinning object make it more difficult to angularly accelerate. So more difficult to spin it up or spin it down. And it turns out, yes, there is. And that quantity is called moment of inertia. So notice the word inertia is in common, right? With the old inertial mass. And this quantity here, which we're going to call capital I for inertia, right? So moment of inertia, this quantity is what fully describes how hard it is to spin something up or spin something down, right? In other words, to make it accelerate in an angular fashion. So first of all, the sort of fundamental definition is given by this mathematical formula right here, which we are not usually going to use for most of our problems. But we'll start here with just sort of laying out what this quantity is. So if we imagine that we have some set of masses, right? And suppose that we can either pretend that they're really small. Let's pretend that all of these masses are sort of point-like. Okay. And suppose that they're all connected to each other in some rigid fashion. So suppose we had masses A, B, and C, and they're all connected to each other with these rigid rods, but the rods themselves have so little mass we can neglect them compared to the three sort of point masses, A, B, and C. Right. Now, in that case, the moment of inertia of this system would be the sum of each of the masses times the distance that that mass is located from the axis of rotation. And specifically, we want this shortest distance, which would be basically the perpendicular distance of each of those little pieces of mass from the axis of rotation. Just quickly, you can see that the units of this quantity I are going to be the units of mass times the units of distance squared, right? So it's going to be kilograms times meter squared in MKS units. Now notice what this quantity is telling us. This says that it does matter where the axis of rotation is that we care about. So for example, if we cared about this blue axis right here that I've drawn vertically, then notice that the distance of mass B and the distance of mass C from that axis are 0. So when we go to add up the three different masses times their distances squared, mass B and mass C would have 0 distance, and mass A would be at a distance of 0.4 meters. So we would have just mass A times RA. Now, pardon me. On the other hand, what if we wanted to rotate this whole arrangement about a different axis? What if we wanted to spin the whole thing around this horizontal blue dashed line right here? Well, then all those distances would be something completely different. Notice that mass B and mass C are now each about 0.2 meters, or I think it's like 0.15 meters each away from that axis. And notice that mass A is also about 0.15 meters away from that axis. So each of those now has a totally different value of RA, RB, RC than they did for the other axis. So that's one of the things about moment of inertia. It depends not only how much mass you have, just like regular inertia, but unlike regular inertia, it depends how far each of those pieces of mass are located from the spin axis in question. So if we take the same object, the same arrangement of masses here, but spin it about a different axis, then all of a sudden its moment of inertia is totally different. And it'll be much harder for us to spin it up or spin it down, depending on which axis we choose. The general thing that we want, that I'd like you to just remember about moment of inertia in general, is notice that if we could take these little masses and move them all farther from the spin axis, then what we would do is we would increase the moment of inertia. On the other hand, if we could take those little masses individually and move them all closer to the spin axis, then we would decrease the moment of inertia. So that's the thing to remember here in the purple writing right here. The farther that on average the pieces of mass are for any particular spinning object, the farther that they are from the rotation axis, the larger the total moment of inertia for that system of masses, okay, or for that extended object, if it's an extended object. But notice there is something that is not in this equation, and that is where the mass is located along the axis, okay? So notice that it matters only if we were to consider our original first axis of rotation, this vertical blue line right here, it would matter how far mass A is from that axis. Right now, it looks like mass A is 0.4 meter. So if mass A were to come closer to the axis, we would decrease moment of inertia. Or if we were to take it farther from the axis, we would increase its moment of inertia. But if we were to move it up parallel to the axis or down parallel to the axis, it does nothing to change the moment of inertia. This is very important to remember as well. Okay, so moving mass along and parallel to a rotational axis does not change how hard it is to spin it up or spin it down. It does nothing to change its moment of inertia or any of the quantities that depend on moment of inertia, as we'll see later, like rotational kinetic energy or angular momentum. All right, now what if, well, okay, we're gonna now talk about some special cases. Let's first consider a special case of a single point-like object. So in that case, there's only mass number one, that's it. It's a single point-like mass, and suppose that it's simply spinning around at some distance r from the rotation axis. This probably looks an awful lot like our uniform circular motion from a few chapters ago. Okay, what would be the moment of inertia then of a single point mass sort of rotating at distance r from its rotational axis? The answer is just m times r squared for that one mass, and that's it. And that is it. Okay, so this is sort of the simplest case, if you want to think of it that way. Right? Instead of having an arrangement of masses or a collection of masses, we just have a single sort of point-like mass. So we can make this assumption when the size of the mass itself is really tiny compared to this distance r. So for example, when we think about the Earth going around the sun, the size of the Earth itself, the Earth is clearly not a point mass, but the size of the Earth itself is so small compared to the distance from the sun that we can approximate it like a point mass when we think about its rotation about the sun. Now let's consider more extended objects. For example, spheres, cylinders, etc. If I go back a couple slides just briefly, what we would really need to do is we would need to take that extended object and cut it up into a very, very large number of tiny little mass pieces. And then for each of those mass pieces, we would have to multiply each chunk of mass by how far from the spin axis it's located. If you've already had some calculus, you probably can sense that this sort of a summation becomes an integral in the case of infinitesimally small masses. In that case, we can add up a continuous distribution of mass all around this object. Okay, if we can describe this object nicely by a mathematical function. Okay. All right, well, fortunately, someone has done all those integrals for us. Okay, so someone has already done the calculus, and the beautiful thing is for common geometric shapes, assuming that this substances are made of uniform density. So uniform density along the rod or this sort of plate or the cylinder. If we assume that it's sort of a uniform density metal or uniform density wood or whatever it might be, then it turns out the moment of inertia for each of these objects reduces to a surprisingly simple formula. So if we want to rotate a cylinder about the axis that goes right through its center, its long axis, if you will, if we want to spin it about that axis, either direction, it will have a moment of inertia of 1/2 times the total mass of the cylinder times the radius of the cylinder. Now, remember how I said it doesn't matter where the mass is distributed along the axis. Notice how the length of the cylinder is not explicitly listed here. The height of the cylinder or the height of the disc or the length of the cylinder, whatever you want to call it, it's not explicitly listed in this formula. All it's listed is the radius of cylinder, which is what governs how far this mass is located from the spin axis. But it doesn't matter where along the spin axis the mass is distributed. Okay, the sort of simple case of if you imagine taking a long exposure of a small object being spun around in a circle, you would see something that looks like a photo of a thin hoop. So a very thin hoop or thin, very, very thin walled cylinder, not low mass necessarily, but just thin thickness wise. So we're assuming that this thickness here is extremely tiny compared to this radius. In that limiting case or idealized case, then it turns out the moment of inertia is just the same as it was for a small point-like object, which is 1 times mr squared. On the other hand, if we sort of distribute the mass all along this distance here, right, then notice how the total moment of inertia becomes smaller because now some of the mass is located closer to the spin axis. So that reduces the overall moment of inertia like we did for the cylinder, right? If we push all the mass as far from the spin axis as possible, then the moment of inertia grows and becomes bigger. 1 times mr squared, like it is for a thin-walled hoop or thin-walled ring. We can consider some additional common cases. If we have a solid sphere, notice the coefficient is small again because a lot of the mass is close to the axis. But if we have a hollow sphere, right, assuming that it's relatively thin compared to the size of R, then notice the coefficient becomes big again because although some mass is close to the axis, a lot of it is located far from the axis, and so on. If we have a rod, right, a relatively sort of thin rod, then it's 1/12 ml squared if you spin the rod about its center, but it's 1/3 ml squared if you spin the rod about its end. Because once again, same length rod, but we've pushed a lot of this mass much farther away from the spin axis. So it increases the moment of inertia considerably. Okay. Just take a quick look at these other formulas and cases. This would be a large slab of material spun about its edge, like a door. This would be like a door on a hinge about its edge. So it would be swiveling around this axis right here. On the other hand, this would be sort of a big, like a book. If you had a thin but large book and you spun it on your finger about its center. All right. Finally, one quick last comment. What if we knew the moment of inertia of, let's say, this big sort of square thing here, and we wanted to spin it about an axis that is parallel to the one shown here. So we already know the formula for the moment of inertia about this axis, but we wanted to spin it about an axis that grazes the corner or an axis that is just piercing the slab in some other location. Well, then we can use something called the parallel axis theorem. So let me take this slide out of order. What we can do is say, if we know the moment of inertia of this shape about some axis that goes through its center of mass, so suppose we already know that for that sort of rectangular plate, but we would rather rotate it about some other axis that's parallel to the first one. Then the parallel axis theorem says you just take the original moment of inertia formula and you add m, total mass of the whole object, times d squared, where d is that separation distance between the two parallel axes. This would be true if the axis grazes the edge of the object, or it could even be an axis that's located somewhere off the object, assuming this whole object is sort of swinging around through space. I don't think that we'll have any problems in our that we're going to encounter in our homework set or on the sample tutorial that will use the parallel axis theorem. But this is such a relatively straightforward formula. It's important for you to know that it exists and it's here in case you need to use it for commonly encountered situations. The other commonly encountered situation is if you can consider a complex object to be a combination of rigidly connected common shapes. So suppose that we have this spinning wheel that we use in our physics lab. This can be approximated as 3 discs that are glued together. The really large disc and then one small disk on this side, and then another small disk on the other side that's invisible. Or you could consider a sort of wheel, like a wagon wheel here, to be one sort of thin ring, and to it you can add four rods that are all being spun about their center. So we can consider the wagon wheel to be a sum of sort of a thin hoop combined with four rods that are being spun about their center. In that case, if you know the moments of inertia of the individual pieces that are rigidly connected to each other, you can just add all of those moments of inertia together, assuming that all of these moments of inertia share the same common rotation axis. Then we just add them all together, and boom, you get I total for the whole object. So this is also surprisingly simple and straightforward to use. So although I don't know that we'll need to use it for any of the problems that we'll do for the lecture, I do know that it certainly applies to the lab experiment. Now, before we, first let's talk about the quantity of kinetic energy. I'm going to develop this formula and many other formulas. Instead of deriving them from scratch, I'm just going to show them to you as analogies of similar formulas that we already know for linear motion or translational motion. So we already know that for an object that's moving through space at some speed v, its translational kinetic energy, as we're going to sometimes call it to distinguish it from rotational kinetic energy, its regular kinetic energy, if you will, or linear kinetic energy, is equal to 1/2 times its mass times its speed squared. If we were to sort of do a substitution, what's our mass equivalent for rotating objects? Right? This is our first use of moment of inertia. So it's going to be capital I. And then we already know that for speed, we have something called angular speed. So for an object that is spinning on a fixed axis, right, where the axis is stationary, but the object itself is spinning about that axis, its rotational kinetic energy is going to be equal to 1/2 I omega squared. Okay, so that's because every little piece of mass of this object has some speed through space. So all the little pieces of mass have some sort of energy of motion, just like for the car as a whole. There's every little piece of the car has some energy of motion. The only difference is that for a car, all of the pieces are all moving at the same speed. But for a spinning object, notice they all have different linear speeds. So that luckily, the math here of that moment of inertia, remember how it had radius squared in it, right? And that takes care of that distribution of all those different pieces of mass that are all at different radii. So we'll see some examples of how this is used when I switch over to do a couple quick examples from the tutorial sheet. Before I do that, I'd also like to talk about a common situation, and that is when you have an object that is both in translational motion and rotational motion at the same time. So on the previous slide, we were considering an object that is just translating or just rotating. Well, what if we have something that's doing both? And a really common example of that would be a rolling object, a rolling body. Like, for example, a wheel or a tire on a car. Okay, if we can forget the rest of the car, if you just consider that part, that wheel or tire, it is both moving through space, translating, and at the same time, it's also rotating about its own axis. So if you're on a bicycle or motorcycle and you look down at your wheel, you see it rotating on its own axis. Okay, so the total kinetic energy of an object that is doing both of those things is equal to the translational kinetic energy of the object. So if we consider this rolling, it could be a rolling ball, or it could be a rolling hoop or rolling cylinder. It's translational 1/2 mv squared through space, plus its rotational 1/2 I omega squared about its own axis. So if you sort of ignore its motion through space and just, let's say you could jog along, so that way you can look at the object as though it were stationary with respect to you, you would just see the omega, right? It's angular speed about its own axis. This would also apply to any other object, not necessarily rolling on a surface, but when its axis is moving through space translationally at the same time that it is also spinning about that axis. So for example, this sort of unspooling ring right here, or if you have a yo-yo and you drop it while holding the end of the string, something like that. Okay, those also would follow the same sum of translational plus rotational energy. in the specific case of an object that is rolling without slipping. So in other words, if the point of contact between the rolling object and the surface is always sort of stationary, okay? So in other words, this would be an object that is not skidding. A skidding car tire, for example, or bicycle tire, is something whose rotational speed is no longer tied to the speed of the surface underneath, right? Because there's slippage at that point of contact. So we're going to consider only the case of an object that has proper grip, right? A car tire that is not skidding or not slipping, or a pool ball that doesn't have some weird sort of backspin or something on it, right? If it's just rolling nicely, right, in some manner that's rolling without slipping, then we can tie together the translational motion of the object with the rotational motion of the object. These two speeds will always track each other exactly, and they will follow this familiar formula that we already know. So if we think back to the relationship between linear speed on, let's say, a spinning object like a merry-go-round or turntable, the linear speed of any point on that object is related to the angular speed of the whole object by how far the point is from the center of rotation, right, from the rotational axis. Well, in this case, we're considering the edge of the object, because for rolling bodies like tires or balls, then we're talking about the point of contact is always at the edge. So this is the full radius of the object, and this would be the translational speed of the center of mass of the object. So that nice condition there, we'll see how handy that is when solving rolling body problems, if we can make this assumption. And this is the only type of rolling body problem that we'll do in this class. All right, so before we move on to sample problems, let's consider just briefly a classic sort of thought problem. And that is, what if we could release several rolling bodies from rest at the top of some sort of a hill? It doesn't need to be a flat ramp. This could be a curved hill or one of varying slope. Which one of these objects, we know that because they have different moments of inertia, they are going to angularly accelerate at different rates. Or put another way, some of these objects are going to be easier for gravity to angularly accelerate than others will. So which of these objects, which will get to the bottom of the hill first, okay, is sort of the classic question, assuming they all start from rest and they all start from the same height. Now notice here, they have a variety of different masses and a variety of different diameters or radii. And the beautiful result that we're going to see is that actually that in and of itself won't make a difference. Instead, it will be their distribution of mass and their moment of inertia distribution that will ultimately govern which gets to the bottom first. Well, what we're going to do is, instead of, you might first think this is a problem that would ask us to solve for the time of descent, right? And then try and figure out which of these objects has the shortest time. So we're going to sort of cheat a little bit here. We're going to instead take a shortcut. We're going to say, instead of solving for that shortest time of descent, let's instead solve for the speed at the bottom of the hill. And then we'll see which one of those objects has the greatest speed at the bottom. And we will be able to infer backwards that the object that has the greatest speed at the bottom must have gotten there in the shortest time. So that will end up allowing us to sort of answer the question in a backhanded way. All right, well, we know that if we don't care about the time of descent anymore, if all we care about is the speed at the bottom, this is a prime situation for conservation of energy, right? So what we're going to do is say, all right, we have the energy at the top of the hill is equal to the energy at the bottom of the hill, and we'll assume that there's no work done by non-conservative forces, okay? So we're going to say that although there's grip friction between the rolling object and the hillside, there's not any air resistance, for example, right? And the object, we don't need to worry about sliding friction because the object doesn't slip, right? So the energy at the bottom is going to be just the rotational energy, the kinetic energy of the object, which will be the sum of its rotational kinetic energy and its translational kinetic energy, which I've written out right here. So this is for any one of the objects. And then at the top, the object has no kinetic energy because it starts from rest, but it has potential energy, gravitational potential energy. So this y initial here was in the diagram over here and on the previous page, this is h, the height of this ramp or hill right here. And again, it doesn't need to be constant slope. It could actually be a curved ramp. It could have varying slope. It doesn't matter. The answer will be the same, right? Because of gravitational potential energy it's path independent. It doesn't depend on the shape of the path between the initial height and the final height. Now, at first glance, the right-hand side of this equation looks like it might have two unknowns. This is the final speed at the bottom that we want to find for each of our objects, but this is a different final speed. This is a final rotational speed, whereas that's the final translational speed. So that might look like one equation with two unknown quantities. But what we're going to do is invoke that rolling condition. We're going to say, we know that for an object that rolls without slipping, its rotational speed is tied to its translational speed by v is equal to omega r, where r is the radius of the body. Then we also know that if we go back to that table of moments of inertia for common objects, we know that the moment of inertia for any common geometric object, at least, is equal to mass radius squared times some pure mathematical number. And that pure mathematical number, if you look at that table, they're always between 0 and 1. So 1 would be the ideal sort of idealized hoop where all the mass is at radius r from the spin axis. And then all of the objects that have some mass closer to the axis and not all of it at radius r will have a coefficient here that's smaller than 1. In our textbook, this is called beta instead of lowercase b, but same thing. It's just this sort of a placeholder for whatever the mathematical constant is for that particular shape. So if we go back to the table, you can find out for a hoop, the value of little b is 1 mr squared, right, for an ideal thin hoop or thin cylinder. But for a solid cylinder, then the solid cylinder has, ignore the empty can for a moment. The solid cylinder is 1/2 mr squared. 1/2, pardon me, is the value of that little b, right, instead of 1 for the hoop. For a sphere, for a solid sphere, it was 2/5 mr squared. And if this cartoon had a hollow cylinder, it would be 2/3 mr squared. I'm sorry, I said cylinder, a hollow sphere. If it had a hollow sphere, it'd be 2/3 mr squared. By the way, one little quick side note, what if we also had like a frictionless box, like an ice cube or something like that, right? Some object that doesn't rotate at all. Then we do a little bit of math, and we find that the and cancel our radius right here. The radius will cancel out. Okay, and we find that the mass cancels out from the entire equation, so it actually goes away completely. And then all we have now is one unknown anymore. We just have the linear speed at the end because we've replaced the angular speed by this expression with the linear speed. Simplifying the equation further, we can solve for the linear speed at the bottom of the hill. We find it depends on the height of the hill, which is the same for all of our objects, assuming they all start their race at the top. And what's gone from the entire equation is the mass of the object and even the radius of the object. And all that matters is this mathematical coefficient b. So what we learn is that the objects whose value for little b is the smallest are going to be the ones that have the greatest speed at the end, and we can infer that they got to the bottom first. Conversely, the objects whose mathematical constant little b is the biggest, which would be when b is equal to 1, right? The smallest value b can have is 0. The biggest value little b can have is 1. So the objects whose mathematical value for little b is 1, which would be a hoop or empty cylinder, then they're going to have the slowest speed at the bottom of the hill, linear speed at the bottom of the hill, and therefore we can infer that they got there last. And it turns out this is exactly what happens. What's also kind of interesting is if we had multiple, let's say, solid spheres of different masses and different radii, but each one of them is a uniform density solid sphere. So you have small ones and large ones. If we can make the assumption that they're all big enough that we can ignore air resistance, right? You could have ones that are low mass, ones that are high mass. What we would find is all the spheres would all get to the bottom with the same speed, and therefore we can infer they got there at the same time. Lagging behind them would be all of the solid cylinders, which would all get there with a slightly slower speed than the spheres, right? But all the cylinders would also arrive at the same time as the other solid cylinders. And then lagging behind all of them would be any hoops, all of which would arrive at the same time, regardless of their individual masses or radii. It's a beautiful final result. And if, what would have actually beaten all the rolling objects would be the frictionless ice cube or any other frictionless non-rotating bodies. Because for them, they don't have to put any kinetic energy into rotation of the object about its own axis. 100% of the gravitational potential energy they start with, which is on the left-hand side of this equation, winds up only in translational kinetic energy, which is this term right here. So they would actually have the fastest speed of all significantly. And they don't have to put any speed at all into any energy, pardon me, into rotational kinetic energy at all. So any non-rotating bodies would actually win the race completely. All right, great. Let's now I'm going to work through a couple of the example problems. Problem 5, which is just about the kinetic energy of a spinning compact disc or DVD. And this is basically a spinning disc or cylinder. And then problem 6, which is if you have a solid sphere like a bowling ball, what is its rotational kinetic energy? And I have a sort of a simple rolling body problem there. So let me switch to my camera. Okay. So I hope now you're able to see the problem number 5 from our tutorial number 25. And just to quickly sort of set the stage. Suppose that we think of a CD or a DVD as being a sort of uniform disk. Okay, so we're going to pretend that it is a solid disk without a hole. We're going to ignore the hole in the middle just to keep the math simple. Okay, and suppose that is a disk with some sort of height or thickness, which is given as 1.22 millimeters. And it has a radius of 60 millimeters. And it has some total mass, which is 16.5 grams. Right. And to save you the trouble of looking up the formula for moment of inertia of a solid disk or solid cylinder, a uniform density cylinder, I just reminded you right there, it's 1/2 mr squared. Now, let me remind you that let's go ahead and solve part A. Part A is asking, what is the kinetic energy of the CD when it's rotating at 20.9 radians per second? Okay, now when you look this stuff up online, a lot of rotational speeds of things like centrifuges or hard drives or DVDs are given in RPMs. So I've already just done the conversion for you, so you don't need to worry about that. All right. Well, we know that the rotational kinetic energy is going to be equal to 1/2 I times omega squared. So omega is given, but we haven't already solved for I. So let's go ahead and calculate that first. I'm just going to do it as a separate calculation instead of just substituting in the formula algebraically. So I for a cylinder is equal to 1/2 mr squared of the cylinder. And this is for when the cylinder is rotated about its central axis like that. Bear in mind that the moment of inertia would be different if you were to flip it end over end like a coin, or if you were to move this axis somewhere else. Okay, this is 1/2. Now let's convert everything into MKS units. So that way our answers can be in joules. Okay. So this is 0.0165 kilograms, right? 16.5 grams. And then the radius is given as 60 millimeters. So I'll convert that into meters. And then I calculate what that is. And that's equal to about 2.97 times 10 to the negative 5 kilogram meter squared. Right? Now, actually, my calculator tells me that that value is exact. So it's 2.970000, etc. Right? It's always, again, this is a 3 sig fig problem, so it's always good to carry extra significant figures. Now we can plug that into our formula over here on the left. So the rotational kinetic energy of this CD when it's spinning at 200 RPM is going to be equal to 1/2 times 2.97 times 10 to the negative fifth. And then omega, we already know, is 20.94 radians per second. So I asked my calculator what that is. And I get 0.006514. Let's round this off to 3 sig figs and convert the joules into millijoules. So 6.51 millijoules. Now, for part B, I ask, how much additional energy would be needed to double the angular speed of the CD? Okay. Now, a DVD or CD player does change the spin rate of the disc as the little read head or laser moves from close to the rotational axis to further out, far from the rotational axis. Right? The reason is because the data that's encoded on it is encoded at a constant, they call it constant linear velocity. So the linear spacing of the data along the CD, it sort of has a constant spacing. And as a result, in order to have it go past the little laser at a constant speed, you need to keep changing omega as the laser changes its distance r from the center. So, so that little motor inside needs to continuously, spin up these CDs or DVDs, and then it has to spin them back down before you eject them. Or when the little read head moves to a different radius, it needs to spin them up and spin them down. So how much additional work is needed or would need to be done to spin this CD up from 200 RPM to 400 RPM? All right, well, let's find out what is the final kinetic energy of this CD at that final 400 RPM. And let's compare that. We'll subtract away from that the initial rotational kinetic energy at 200 RPM. So let's take the rotational final kinetic energy. And one way for me to answer this is to just plug in all of the values. So I'll tell you what, I'll do that first. But then before we move on, I'm going to revisit this question and show you how the faster way to answer this would actually be with just proportional reason. Well, tell you what, let's do that first. Okay. We know that we want to double the angular speed. So if I were to double the angular speed omega, what should happen to the rotational kinetic energy? We've already calculated what it is for 200 RPMs. So what should it be for 400 RPMs? Well, if the rotational kinetic energy depends on angular speed squared, doubling the value of the angular speed and leaving everything else constant should quadruple the size of the rotational kinetic energy. So without doing any further calculation, I should just be able to take this value and quadruple it. And that's equal to 26.06 millijoules. The other way to solve this would be to go through and actually plug in all of the values. So this is going to be 2 times the value of omega initial that we have up here. Okay. So then that would be 1/2 2.970 times 10 to the negative 5 kilogram meter squared. And then I have 2 times 20.94 radians per second squared. Oh, the whole thing is squared. Okay. So the square applies to the 2 as well. And then I asked my calculator what that is, and behold, it's the same answer, 26.06 millijoules. Okay. So you can see how using proportional reasoning here, right? If we wanted to just double the value of omega, that should quadruple the value of K rotational. And I can do that quickly and easily without much further calculation, basically just taking the original value and multiplying by 4. All right, now we can try and actually answer the question, which is asking what is the increase in energy? So how much work would need to be done, right? In other words, what's the increase in kinetic energy? So let's find out what is delta K. That's going to be K final minus K initial. And all of these are rotational kinetic energies because the object is not moving through space with any translational kinetic energy. The axis, the rotational axis is fixed, right? The spindle that the CD or DVD rotates on is fixed in space. Well, that's just going to be 26.06 millijoules minus the original 6.51 millijoules. And when I find out what that is, that's 19.5 millijoules, rounding to 3 sig figs. Okay. So that's the increase in kinetic energy as the object spins up. Okay. So in other words, you have to put in, if it had a certain amount of kinetic energy at 200 RPM, we have to put in 3 times more than this to get it up to 4 times that amount. And so we added the 3 times more, and it will get it up to 4 times that amount for the new 400 RPM kinetic energy. But to answer the question, we have to add an additional 19.5 millijoules. All right. Let's shift gears now to question number 6, and that will conclude this recording. So question number 6 is a rolling body problem. So suppose that, and actually it's sort of 2 questions. It really is 2 separate questions. So I might sort of start a fresh page between parts B and part C. So for parts A and B, let's suppose that we have a bowling ball and it's rolling without slipping along some sort of flat surface, or, well, it doesn't matter. All we know, this is at an instant in time. Okay, at some instant in time, we're told that it is rolling with a translational speed of 2.5 meters per second. And we're told that it has a radius of 11 centimeters and a mass of 4.5 kilograms. And I remind you what the formula is for the moment of inertia for a solid sphere. So we're asked, okay, knowing that this bowling ball has a particular translational speed that's given, so that value is given here as 2.5 meters per second, you're asked what is the angular speed at that same time. Okay. Assuming that it's rolling without slipping. Also, at that same time, you're asked, what is the total kinetic energy of this rolling bowling ball? So notice this is a rolling object. So the kinetic energy will be the sum of its rotational and its translational kinetic energies. All right. Well, we know let's answer part A first and part B, and then part B. And then I'll leave part C as a totally separate problem. For rolling without slipping, we know that the translational speed, right, of the center of mass of the bowling ball is just going to be equal to the angular speed times r, where r is the radius of the bowling ball. So that means the angular speed is equal to the linear speed divided by r. So that's going to be 2.5 meters per second divided by the radius, which is given as 11 centimeters. So if I calculate what that is with my calculator, I get 22.7, et cetera, radians per second. Now I'm going to keep this extra sig fig here for use in later calculations like the total kinetic energy. But for the purposes of just answering this question, we need to round to 2 sig figs. So that's about 23 radians per second. Okay. If that's going to be a final answer. Okay. But I want to keep this value here with additional sig figs for use in other calculations. Again, to prevent round off errors. Now to answer the second question, what's the total kinetic energy of this rolling body? So the total kinetic energy is going to be equal to the translational kinetic energy plus the rotational kinetic energy. So we have both forms of energy of motion happening at the same time. That's going to be equal to 1/2. Sorry, that's 1/2 total mass of the bowling ball times v squared, where this is a translational speed, plus 1/2 moment of inertia of the bowling ball times angular speed, omega squared. We know all of the quantities up here so far, except for I, the moment of inertia. So let's do a little side calculation here and figure out what that is for the bowling ball. And then we'll be able to plug it into the formula here for I. 2/5, pardon me, mr squared for a solid sphere. We're given the mass as 6.5 kilograms, and we're given the radius as 11 centimeters. So the moment of inertia of the bowling ball is, now I'm going to keep, again, I'm just going to keep extra digits on this intermediate value here. Now I can use this in the formulas on the left-hand side. So now I can plug in all of these values here. Here's the mass, translational speed, moment of inertia, and rotational speed. Don't forget to square both of those speeds. Now I can just ask my calculator what those quantities are. I'm going to show them to you separately on the page before I add them together, just because it might be worth taking a quick note about, for this rolling bowling ball, how is it distributing its energy between its translational motion through space and its rotational motion about its own axis. And interestingly, if I look at this, it looks like its total kinetic energy is about 28 joules. Notice how it has about 20 joules of translational energy and about 8 joules of rotational energy. So if I look at the proportion, there's a little over 2/3 of its energy, maybe almost 3/4 of its energy in translational motion, and about 1/3, maybe slightly less of its energy in rotational motion. This isn't true for other bodies. For other objects, it might be closer to 50-50. But for it all depends on what this coefficient is here on the moment of inertia. For a solid sphere, this coefficient is 2/5, which is relatively small. But for a hoop, like if you had a rolling hula hoop, then these two would be in almost equal proportion to each other. It would be like 20 joules plus 20 joules. Great. All right, so that's the answer to this question. What's the total kinetic energy of the ball at this moment right here? All right, now this is totally a totally different scenario coming up in part C. So the only thing that it has in common with the original part is it's the same bowling ball. So it has the same mass, the same radius, and the same moment of inertia, right? Which depends on the mass and radius. So we can borrow those pieces of information from up above. But now let's take a look at part C, which is a totally different question. All right. Suppose that this bowling ball is released from rest at the top of a hill of some sort of varying slope. Okay. And then it descends to the bottom of this hill, right, which has a total height of 2 meters. So it descends through a vertical height of 2 meters, right? And well, actually, maybe it's not at the bottom of the hill, but whatever. It has descended through a vertical height of 2 meters, having started from rest. And the question is, what is its linear speed at that moment? So we can consider a hill of varying slope. And suppose that we're going to call this the initial position up here. And it starts with rest. Then it rolls down through a vertical height of 2 meters. Okay. So we'll say that this is 2 meters right here. I'll call it capital H. And at that moment, I'm asking, what is its final linear speed? Now, at that same instant, it also has some final angular speed, right? But the problem is just asking, what's the final linear speed? So we'll call this the final moment. So we have this initial moment up here, and then we have this final moment down there. So again, this really looks and smells an awful lot like a conservation of energy problem, doesn't it? So let's do that. Let's use conservation of energy. We can say that the total kinetic energy, change in kinetic energy, pardon me, plus change in gravitational potential energy is equal to the work done by non-conservative forces. And what I'm going to do is say, all right, suppose that there's no air resistance, right? There is contact friction, so it can roll without slipping, but there's no other sort of drag on the object, okay? In other words, gravity is able to we're able to turn all of that gravitational potential energy into, or work done by gravity, into kinetic energy. All right. So let's say this is going to be K final minus K initial on the left-hand side, right? Delta is always final minus initial. And then what I'm going to do is move this over to the other, well, all right, let me write one more line here. This is going to be equal to M times G times negative delta Y. Okay. So this is, well, actually, no, I'm sorry, it's not negative delta Y. It's just delta Y, which is Y final minus Y initial. Pardon me. The minus sign will show up in a moment. Okay, now we know that the object starts from rest. So this initial kinetic energy will be 0. So let me go ahead and set that equal to 0 now. So I have less to write on the page. The final kinetic energy at the bottom is going to be the total kinetic energy, right? So this is going to be K translational final plus K rotational final. Right? So that all goes into that term right there. And then the change in height, I already know Y final minus Y initial, right? Final is below initial. So therefore, that's going to be equal to negative 2 meters. So negative times negative h. So it would be handy for me now at this point to move this to the right-hand side of the equation. So let me do that. It's going to be 1/2 m v final squared, 1/2 I omega final squared. And I'll move this over to the right-hand side. Now, once again, we have this odd situation where we want to find the linear speed, which we can see is right there. There it is. That's what we want to solve for right there. But we're also stuck with this other unknown quantity, which is the final angular speed. But fortunately, we know that those two are tied together, right? So what we can do is we can plug in the rolling condition. For an object that rolls without slipping, we can say that omega is equal to omega is equal to V over R. So this is our translational speed through space, and that's the radius of the object. And that should give me my angular speed. And at that point, we will know everything in the equation that we need to know to be able to solve for, so we're going to plug that in, to be able to solve for our unknown that we want, which is V final. So let me show you what I mean. Now, technically, we already know I from up above. We've already solved for it up there in the previous part. In fact, we know the numerical value is 0.03146 kilogram meter squared. And this is now going to be V final over R. So at this point, everything that's in the equation is known except for one unknown. So there we go. At this point, I could, if I choose, plug in all the numerical values I know for everything: mass, G, height, R, radius, and just solve for V final. And we would get the right answer if we did that. So we could do a whole bunch of math, and we would get that V final is equal to about 5.29 meters per second. And if I look at the values here, it looks like it's sort of a 2 sig fig problem. So I bet I should round this to just 2 sig figs. What I would like to do, though, is I'd like to show you a small variation on this which is something that we usually do or often do with these rolling body problems. And that is to, let me move my paper down a little more. And that is, instead of plugging in all of these values for the mass and for the moment of inertia and for the radius, we can do something similar to what I did in that example I showed with the rolling race, where many of those quantities, masses and radii, are going to cancel out. And what we're going to do is we're going to plug in a value for this moment of inertia. So we know that the moment of inertia should be 2/5 mr squared for a solid sphere. So let's instead do that, do a little more algebra, and it will ultimately, in the end, make our final calculation simpler. Initially, it'll look a little more complicated, but believe me, a lot of things are going to cancel. So this is the value for I right here, okay? So once again, this is I. And this was omega from the rolling condition. Now, first, we can cancel out this r squared with that r squared. Rewriting the next line. This, by the way, this 2 here also will cancel coincidentally, which is nice. Becomes 1/5 m v final squared. So remember, we still have that squared there. Now we can do 2 more simplifying things. We can divide through by the mass of the object. So notice in the previous line, the radius of the object vanished, the bowling ball. And in this line, the mass of the bowling ball vanishes. So both of them have canceled out. And we're left with 1/2 plus 1/5, these sort of pure numbers here, times v final squared is equal to little g times h. So we could go all the way and simplify it all the way down to, okay, so 1/2 plus 1/5 is 7/10. So this whole thing becomes 10/7 gh square root. And I can go ahead and plug in what that is. Take the square root, and that turns out to be about 5.3 meters per second. That's the final answer. So, you don't have to do this algebraic shortcut like this, right? But it is kind of nice. So I wanted to show you that for some of these rolling body problems, it's an option. And sometimes it gives a beautifully general result, because notice this answer would be the same for any solid sphere that has rolled down a hill of any slope through a height difference of 2 meters, starting from rest. It would, any solid sphere, so a marble or a ball bearing or a bowling ball or any other solid sphere of uniform density will be going 5.3 meters per second after it has descended from rest through a height difference of 2 meters. A beautifully generic result, right? As opposed to up here where it looks like it's a result that applies only to this one bowling ball. So it doesn't seem quite so general. All right, great. So that was the answer to part C. All right, so that was sort of a longer explanation and solution. At this point, there aren't any more rolling example problems on this tutorial, but there are a few in the Mastering Physics homework set. So I encourage you to try some of the problems there.